Hello friends, welcome to the next lecture on the probability and statistics. Today we will discuss about the Laplace distribution. Myself, Dr. Garg, working in the School of Mathematics, Thapar Institute. So what is the content behind this today's presentation is we will see what is the overview of the Laplace distribution, what are the various types, how you can find the PDF, CDF, what is the mean variance, MGF, characteristics function, all about in this video. So what is the overview about the Laplace distribution is? It is a continuous probability distribution function which is defined by P.S. Laplace, which is born and died in this is are there. Now you can see that this, what is the major feature about this Laplace distribution is it is just like the normal distribution, as it has only the one peak, that is called as the unimodal, and the symmetric distribution. But the difference between them, normal and the Laplace, is this Laplace distribution has the sharper peak than of the normal distribution. We will see in the graphical representation in the couple of slides. This Laplace distribution is nothing but the difference of the two independent random variable. If I say x and y are my independent, and if I say this is a follow exponential distribution with here, then the difference of them will follow the Laplace distribution. That is the basic property of this Laplace distribution. It is used to model the phenomena whenever there is a heavy tail or whenever they are higher peak than of the normal distribution. Also, this Laplace distribution is called as the two exponential distribution. One is called as the positive and the negative. Why? Because the graphically look like, say, the two exponential distribution back to back are there. How we can see that this is a double exponential distribution? So any random variable x is said to be the Laplace distribution or the double exponential Laplace distribution with the two unknown parameter mu and b if the probability density function is defined like here, where mu is called as the location parameter and b is called as the scale parameter. So as the suggested that this is the location parameter and the scale parameter, you can see it is denoted as a x. This means the follow. X follows the Laplace distribution with the parameter mu and b. The graphically representation of here, you can see this red color is here, that is mu is 0, b is 1, while this black color is when mu is 0, b is equal to 2, and this is when mu is my minus of 5. You can see that the position are shifting to each other. So that's the meaning of that. Mu is my location parameter and b is my scale parameter. You can see that with the changes of the b, the scale are changes. And you can see whenever b is 1, the peak of this is very high as compared to the normal are there. Also you can see this part is called as the exponential graph. This part is also the exponential graph. That's why this is called as the exponential distribution. All of you know that this is the exponential distribution. So if you draw the graph like this way, so this is the double exponential or called as the Laplace distribution. On the other hand, there is another form called as the standard Laplace distribution. What is the meaning of that is, if I substitute here as mu is 0, b is my 1. That means this Laplace distribution will convert it into the standard Laplace distribution. So you can see whenever I just mu 0 b 1, then this becomes my 1 by 2 e raised to power minus of mod x. So that is the standard Laplace distribution. So I denoted here as a y because x I used in the previous one. So y follows the Laplace distribution with the parameter 0 and 1. Now what is the relation between the double and the standard distribution? These two types are there. So if I say if x follows the Laplace distribution, then y, that is x minus mu divided by b, follows the Laplace here. That's very simple how you can prove that. So since your target is to find the PDF of the y, so we can use the PDF of y by using here. So what is the f of x is? This f of x is here. So the PDF of this x is given by here. Now you need the dx upon dy. So from here, can you find the value of the x? You can easily find the value of the x from here. So therefore dx upon dy, what is the value of the dx upon dy? That is nothing but the b. You can substitute the value here. What is the value of y? What is the value of this? This is nothing but my y. So this is here. So this b will be cancelled out. What is that? This is nothing but my Laplace distribution of 0, 1. So that's the relation between this here. You can see if y follows the Laplace distribution of 0, 1, then this x will follow the Laplace distribution of mu b. You can easily find the value of the y from here, that is like here. So that is a vice versa are there. Now how you can find the CDF of the Laplace distribution? So we know that this is a Laplace distribution of the standard. So we can firstly find the standard and then we will find here. Our target is to find Laplace CDF of this. Since it lies in between here, so our target is to find over these two domains. The first domain is whenever y is less than 0, that is here. The CDF definition is here. You can write like this way, 0 to y of this function. What is the value of the, whenever y is lies between minus infinity to 0, what is the value of this? This is nothing but my plus of y, because whenever y is less than 0, what is the value of this? This is nothing but my plus of y. So therefore this is e raised to power y. After the integration you will get as of this answer. Now whenever y is greater than 0, what is the answer of whenever y is greater than 0? What is that part? This is nothing but my minus of y. So I can discretize this over minus infinity to 0 and then 0 to y. So you can see minus infinity to 0, 0 to y, minus infinity to 0 is this answer, and after the solving you will get here. So therefore you can substitute this value, you will get the CDF of this standard Laplace distribution. Also you can find the Laplace CDF of the double exponential. What you can do is you can simply replace whatever the y is there, you can simply replace y as of x minus mu upon b. So you can see I replace this y as x minus, I can replace y this as here, I can replace here x minus mu upon b is less than 0. What is the meaning of that? X is less than of the mu here. Similarly for this is the CDF of the double exponential distribution. This is the graph of the double exponential distributions are there whenever mu and 0. So this is the graph corresponding to the standard, while others are corresponding to the others are there. How you can find the mean and the mean and variance of the Laplace distribution? So we can start with the standard Laplace and then we will find the double exponential. So our target is to find the E of mu and Ey square. So I can start with here. Clearly says that you can see whenever r is 1, that is becomes the E of y. When r is equal to 2, then we will get here. So we can start from here. Now this mod of y is from minus infinity to plus infinity. So I can discretize this from minus infinity to 0 and 0 to infinity. What is the value of this when it's minus infinity to 0? It's a plus of y here and this. Now you can see about what is that. Do you remember that which is the integration of this? Yes, this is nothing but my gamma function, that is my here. How you can become a gamma function? That's a simple, we need e raised to power minus of this. So if I take y as of say minus of z, so what is that? Dy is nothing but my minus of dz. What are the limits are there? Limits are my from infinity to 0. This is my minus of z raised to power r, e raised to power minus z dz upon. So I can adjust this negative with the limit changes are there. So I can change the limits. This is minus z raised to power r, e raised to power minus z of dz. So I can write this expression in terms of here like this way, or I can simply take y as of the minus y. Now I can take minus 1 raised to power r is a common, that's outside. What is that? This is nothing but again gamma function of r plus 1. So you can see expected value of the y raised to power r is my here. Therefore you can substitute the value of r is 1. You can get what is the r is 1? It's become a 0. So e is 0. What is that? Whenever r is equal to 2, if r is 2, then it becomes a 1. Gamma function of 3 is nothing but my here. You can substitute the value this is my 2 minus of 0 square. So the variance is my 2. So what you conclude that whenever you have the standard Laplace distribution, mean is 0, variance is my 2. Now by using here we know the value of the y. Can you find the mean of the x from here? You can easily find the mean and variance of the double exponential. This is my nothing but expected value of this. What is that? This is nothing but my here. Expected value of y is my 0. So the mean of this double exponential is mu. Similarly you can find the variance of the y, which is nothing but my b square of this. This is here. So what you conclude that that is whenever here. So for this distribution, mean is my mu and the variance is my 2 times b square. Again clearly sees that whenever mu is equal to 0 and b is 1, then this is converted to here. How you can find the moment generating functions of this Laplace distribution? So we all know that moment generating function is my here. I can start on the Laplace distribution and then we can easily find the double exponential here. We can start from here. Again I can break this interval into the two parts from 0 minus infinity to 0 and 0 to infinity. You can see this is a positive, this is a negative. So how you can solve that? This is again very simple. So this is the base are same, so I can write this as 1 plus t of y of this is a dy, and similarly I can write this expression as here. So once you write here, this is my y. So once you will integrate them, so what is that? This is nothing but here. So when you substitute the value of this, what will happen? This is my e raised power 0 is 1 and e raised power infinity is my 0 plus half. This is e raised power infinity is 0 minus minus plus upon here, provided this value is my positive. That is provided this value is my positive, because if this is a negative, then when you substitute infinity, it's a positive. So e raised power infinity is my infinity. Similarly for here. So now what is that? After the calculation, you will get this value as of here. So how you can relate them? This is nothing but my mod of t is less than of 1. This is the moment generating function of standard Laplace distribution. Now we can find the Laplace distribution of the moment generating function again by using here. We can substitute the value of the x here. This is t of mu plus b t of y. This part is constant. You can see this part is my constant with respect, so it can be taken as of outside. So what is that? This is b t of y. Now what is that? How you can write that? This is nothing but my moment generating function of the y with the parameter of here. Now we know that moment generating of y is my here, so I can replace simply b with respect to the tb. So that is a t square. It means here, provided tb is my less than 1. That's the moment generating function of double exponential. Similarly, we can find the characteristics function of the Laplace distribution. Again, we can find for here, and we can easily derive the double exponential. What is the definition of the moment characteristics function? Is phi of y is e raised power I tx. So I can use this again, minus infinity of this iota ty of f of y dy. Again, this f of y is nothing but my here. I can again break this into the two parts, from minus infinity to 0 and from 0 to infinity. So I can write like here. I can take the common like this way. Now you can integrate this again. This is with respect to y. So this is with respect to y. So when you integrate them, you will get this expression as of here. Again, you can substitute the limits. So when you substitute 0, it becomes my 1. If infinity, it becomes my 0. So this will be here. Similarly, you can find the Laplace characteristics function of the double exponential like here. You can substitute the value of the x from this. You will get this expression. This is nothing but by again this is again the characteristics function of the phi of iota t of b. So that is the simple expression. You can use this expression, substitute the value as of tb in this case. So this is the way you can solve the characteristics function, moment generating function, and all that. We will see in our next class how you can define the properties of the Laplace distribution, such as if x follows the Laplace, kx plus c will follow here. If x follows the Laplace of this, and so on. So we will derive this in our next class. Till then, you can simply follow this link for finding the various videos. Best of luck, students. Happy learning.